In this video, I introduce guided causal learning for robots. Guided causal learning is a trajectory-centric inverse reinforcement learning method. Suppose the expert generates a trajectory tau by using stochastic and suboptimal policy. An agent learns expert policy by extracting real-world function from expert demonstrations. We use loss function C to indicate the difference between the learned trajectory and the expert trajectory. The probability P over the trajectories tau and the learned policy is defined as an exponential of the loss function. Because this loss, because this loss is larger, then this probability is smaller. That means the learned policy is far away from the expert policy. We can observe the state and the action from the expert behavior. However, we cannot observe the real-world function from the expert behavior. That's why we need to use the inverse reinforcement learning to find the real-world function from the expert demonstrations. Suppose expert runs a real robot system to generate the demonstrated trajectories, and the agent uses the learned policy to generate a trajectory on the robot system that are used to improve the policy and estimate the partition function. The idea is to match sample distribution under the learned policy with the maximum entropy to the distribution under the expert policy. An agent uses the learned policy generate a distribution Q that is used to estimate partition function Z. From his definition, this partition function is an integral of this exponential of the loss function. So we need to find this unknown loss function to estimate, to make this Q close to the expert distribution. Then the entropy loss function also is a negative log likelihood is defined as this L. This theta is a model parameters. If we use a neural network to express the trajectory and his loss function, then this theta is a network of parameters. So from his definition, we have this loss function and split it into two terms. And the second term is the partition function. And then now we use this sum to replace this expectation. And we substitute this Z to here get this exponential. Then now we use a small trick times this Q and divide by this Q. And then we use the Monte Carlo integral. We use sample over the sample distribution and the learned policy to approximate this integral. That's why here we use approximation here, because we use M samples to approximate this integral. And here again, this theta is model parameters. If we use a neural network to express this trajectory and his loss function, and this theta is network parameters. Here we use this theta as the, for example, initial distribution and estimate this loss function from input. And then use this loss in reinforcement learning to find the policy. And under this policy, we generate a trajectory. Use the trajectory and the expert trajectory, we got this gradient. Use this gradient to train the network step by step. Finally, we got a convergent model parameter theta. From a model parameter theta, then now we can estimate the final loss function. To use the gradient descent method to train the neural network we need to calculate the gradient of the loss function with respect to multiple parameter theta. And then we get this the gradient of the loss function include two terms. One is related to the export demonstration. One is related to the learned policy. And then we use this gradient to train the neural network. Finally, we get convergent model parameters. From the model parameter, we can find the final loss function, and then I use the loss function in the reinforcement learning to find the optimal policy. That's our goal of the inverse reinforcement learning. Here is the idea. For example, here is the human, or we the expert run real robot system generate this distribution, and from the initial distribution, on this robot we generate this distribution, and then we use these two distributions. We optimize the cost function and train the neural network to get this model parameter theta. From this model parameter theta, we get this loss function, and use this loss function in the reinforcement learning to find the policy. And this policy, we generate the new distribution. And then we use this new distribution with the expert demonstration together, optimize this loss function again, get the new model parameters and get the new loss function. And iteration by iteration, finally we get the final convergent model parameters and get the final optimal policy. For more details, please check with this reference. Thank you.